Our main goal is still to study methods, to calculate areas of regions enclosed by parametric curves of the xy plane. In the previous video, labeled as Part 1, we discussed a method of calculating the area of a region enclosed by a parametric curve of the xy plane. We shall now attempt to calculate the area of the same region, by using another method. In this method, we try to connect the x and y coordinates of the parametric curve, into a single formula that expresses y as a function of x, if possible. Alternatively, if this is easier, we will seek to derive or find a quadratic equation relating x and y. Without further ado, let us recall the problem under discussion. Below we see the coordinates of the parametric curve C. Since both coordinates are defined by trigonometric functions, we aim to combine them using basic trigonometric identities to find a direct Cartesian relationship. The basic Pythagorean identity applies in our case, since it connects cosine of t with sine of t. X-coordinate is 2 cos of t. And it's very straightforward to substitute it in the expression of the y-coordinate. After that, some simple operations give us the expression of y-coordinate in terms of x. Now, as we can see, the parametric curve is described by the graph of two functions y1 of t and y2 of t, defined on the same closed domain from -2 to 2, and one function is the negative of the other, meaning y1 of -t equals to -y2 of t, for all t in the domain. That is something we were expecting for, since a closed parametric curve cannot be expressed by a single function, because a single function must assign at most one output for each input. For a closed parametric curve, however, different input values for the parameter can produce the same coordinate output, which violates the definition of a function. Also, for all t in the closed domain from 0 to 2 pi x of t is in -2 to 2. So y1 and y2 are real functions of x, with -2 less or equals to x less or equals to 2. So y1 of x is the real function of x that its graph describes, coincides with the upper, green-colored, scale of the parametric curve C. That is, function y1 of x gives the y-coordinates of the upper portion of the parametric curve C, as shown by the green-colored scale. y2 of x corresponds to the lower orange-colored scale. And as we did in part 1, since this egg-shaped oval is symmetric as to x-axis, we only have to find the area of the upper region and then multiply by 2. Function y1 of x is differentiable in the domain -2, 2. So the area enclosed by the graph of y1 and the x-axis is given by the definite integral of y1 over the -2 to 2 domain. Now, in order to save time, please see the way we follow to calculate the area under the graph of function y1. So finally, the area of the region enclosed by the parametric curve is 2 pi. The equation relating functions x of t and y of t is sometimes readily apparent and simple to derive. But in most cases it's not easy, or it's very difficult, even almost impossible, to find any connection between them. For example, for the parametric curve that lies below. By setting x equals to x of t cosine of t minus sine of t, and y equals to y of t equals to cosine of t plus sine of t, with t in the 0, 2 pi closed domain. It's easy to see that curve C represents a circle, centered at the origin and with radius square root of 2. On the other hand, below are some cases of parametric curves for which finding a connection between the x, y coordinates is very difficult. In such cases, as the above, we follow other methods. Below there are some exercises for further study.